in the today's video, we are going to discuss about another technique for image segmentation that is known as local thresholding, that is based on similarities. So till now we discussed about the global thresholding operation, dynamic or adaptive thresholding operation, and we also discussed about optimal thresholding operation. We have seen in the global thresholding a threshold value is selected where the threshold value depends only on the pixel intensities in the image. Where in the case of dynamic or adaptive thresholding, it not only depends upon the pixel value or the intensity values or the pixel in the image, it also depends upon the position of the pixel in the image. So the threshold for different pixel in an image will be a different in the case of adaptive or dynamic thresholding. And in the case of optimal thresholding, we have tried to find out threshold by assuming that histogram of an image is a representative of probability density function of the pixel intensities values. So now we are going to discuss about local thresholding operations, where we will consider in addition the pixel value and the intensity values, its location also. So we will consider the local neighborhood properties. So as you can see in this figure, there is an object which is represented by the dark intensities, and there is a background which is represented by the lighter intensities. So if we are going to plot a histogram of this one, we can clearly see that it is a bimodal histogram, which is tall, narrow and separated by a deep valley. In addition, these modes are symmetric. So symmetric means they occupied same area. The same area is occupied by the object as well as background. So a selection of good threshold value is very simple if there is a deep valley, clear deep valley. So in this case, we do not have any trouble to select the threshold value. But in most of the cases, the histogram is not so clear as we shown in the figure, this figure. So for example, in the next case, we have an object represented by a darker pixel and background represented by a lighter pixel. So now if we plot an histogram, you can clearly see that the background intensities are more dominant and there is a no clear threshold value that will segment this object. So you can see that the contribution to the histogram by the object pixel is almost negligible because the number of pixels belongs to the object is very small as compared to the number of pixels belongs to a background. So now we have to solve this problem. So this problem can be solved if we, instead of considering all the pixels in an image to produce the histogram, if somehow we can identify the pixels which are either on the boundary of this object or near the boundary between the object and the background. So in a sense, what we are trying to do is that given an image with an object inside. So if we plot an histogram of this one, this object and the surrounding neighbor pixels, then we can clearly find a bimodal histogram. So if we consider only these pixels around the boundary to form an histogram, the advantage in this case, we are considering only those pixels near the boundary to form the histogram. Hence the histogram is symmetric in nature. That means the area of the pixels within the object region, this way, this one, and the area of the pixels within the background region are being considered to form the histogram, since they will be more or less same or almost same. So our histogram will be more symmetric in nature. So by considering only those pixels around this narrow strip, so by considering only those pixels around this narrow strip, we will get two advantages. One is the probability pixels to the background and the probability of the pixel belonging to object are nearly equal. At the same time, the area of the object region and the area of the background region, which is used for the computation of histogram, is almost same. So that will make histogram symmetrical also. Once we have this kind of histogram, then the thresholding operation is very, very simple. For this approach, we have to know that what is the object boundary. To draw this histogram, we have to know about the object boundary. And that we do not know, because the basic purpose of the segmentation, that is the basic purpose of segmentation. So we are trying to find out the boundary between the object and background. That is our aim. Once we will get this one, we will get this kind of histogram. So there will be a clearly deep valley here, so we can select a perfect threshold value. Now, to know about the boundary of the object, we are going to use the concept of gradient and Laplacian that we had already discussed in our previous videos. The gradient is used to determine the boundary, and the second derivative is used to find out whether the point lies on the darker side or the bright side of the edge. So this represents the darker side and this represents the brighter side. So as you can see, when the point lies on the darker side, then its Laplacian is positive, or second derivative is positive. And when it lies on the brighter side, then its Laplacian is negative. As in our case, we considered object as a darker and background as a lighter or brighter. So if the pixel belongs to an object, then its Laplacian is positive. If the pixel belongs to a background, then its Laplacian is negative. And edges information we will get with the help of first derivative. As you know that gradient represent the maximum change in intensity or maximum rate of change. If we assume that an image object is dark, background is white, if the gradient value is greater than or equal to some threshold capital T, we assume that this point belongs to edge point. Since points near the edge, the gradient will be high. So gradient measures the rate of change, maximum rate of change. So that will be happen near the edges. If the gradient value is less than some threshold capital T, we assume that this point does not belongs to edge point, not even within a region or near the edge. Now, Laplacian is positive for the object pixel and negative for the background pixel. That comes under the assumption that object is dark and background is bright. So f of x comma y represents the object, del of f x comma y represent the gradient, and del square f x comma y represent the Laplacian. So if f of x comma y is equal to 0, if gradient is less than certain threshold value, so it does not belongs to an object or near the pixels that are near to the object. if f of x comma y is equal to positive, if delta f or f of x comma y is equal to positive, if gradient is greater than or equal to certain threshold value t and del square f is greater than equal to 0. So positive represent the object pixel and f of x comma y is equal to negative if delta f or gradient is greater than equal to t and del square f is less than 0. Since we know that Laplacian is negative for a background pixel, but that is true under the condition when object is dark and background is white. So f of x comma y is equal to 0. Pixel does not belongs to object or boundary or between the object and boundary. F of x comma y is positive. Pixel belongs to an object region. If it is negative, then pixel belongs to a background region. So if this is an image, we are going to scan it, this image. So once we are going to scan it from here, then we can find that this one is corresponding to a background. Now once we are going to scan from here to here, so there is a maximum rate of change of f. So gradient will change. So it will become from negative to positive. Negative is corresponding to the surrounding pixel which is in a background and positive is corresponding to the object. Now again we are scanning through this object, so it will be either 0 or positive. Once we are going from here to here, then it will became from object to background. So that will from positive to negative. Then outside the local region it can be positive, negative or 0. So this star represent any combination of 0, positive or negative. This is corresponding transition from background to object. This is corresponding within the object and this correspond to transition from object to background. So this is an example of local thresholding. So in the next lecture we are going to discuss about region growing and region splitting and merging. That is also based on similarities. Thank you.